My research is on multiple sclerosis, and multiple sclerosis is a disease that affects the central nervous system. And the central nervous system, if you look at this figure, the function of it is to transmit electrical impulses throughout the body. And most neurons actually have a coating on them called myelin. And this myelin is a fatty material. And it's analogous to, for example, a situation where we have a wire cord. So the business end of that wire cord is actually the wires themselves. But in order to conduct the electricity down that cord, you have to have the rubber on that cord, otherwise you won't get proper conduction. And that's the function of the myelin. The myelin is there to insulate the nerve and allow for proper conduction of the electrical impulse. And what occurs in multiple sclerosis is that your own immune system actually attacks that myelin, removes it, causes demyelination, and because of that you are not able to conduct electrical impulses, and that may affect your vision, your mobility, your balance, any number of things. The average age of onset is around 20 to 40, so this disease affects people in the prime of life. It is more common in women than men, about a ratio of approximately 2 to 1, women to men. The symptoms are extremely variable, and that really determines where in the central nervous system you have this demyelination. It also, the symptoms can be quite severe. So in terms of mobility, many times people are wheelchair bound due to increased disability over time. And the reason for that long-term disability is actually the myelin itself can come back on. You can remyelinate, okay? So you can gain function back. But when I use the example of the cord, if you were to cut the wires of that cord, you no longer will be able to allow electricity down the cord, correct? Same thing occurs with multiple sclerosis. You get axonal transection, you get the process is cut. In multiple sclerosis, it appears that the immune system actually is involved in an attack of the brain. And normally, there is very little immune activity in the brain. Occasionally, you'll have immune cells come from the periphery and move into the brain, but they're mainly there for surveillance. They look around. If they don't see anything that is a problem or that they need to remove from the system, they will actually just move back out of the brain. In situations like bacterial infections of the brain or viral infection of the brain, you do have cells in the brain called glia. These are microglia and astrocytes, and they can become activated and they will actually remove those pathogens, the bacteria, the virus, from the central nervous system. And they do this by producing a number of molecules that are toxic to those pathogens. However, in situations like multiple sclerosis, you actually get chronic activation, chronic inflammation, and those same molecules that the brain is producing to get rid the brain of bacteria are actually toxic to the host cells. And so long-term disability in multiple sclerosis is determined by this autoimmune process. It's not completely clear what causes it. It's believed to be autoimmune in nature. That is, that your own body, your own immune system that is there to protect you is actually recognizing something in your brain as being foreign and attacking your brain. Okay? And this leads to the demyelination and this axonal transection and disability. So there's multiple forms of multiple sclerosis. The most common is relapsing remitting disease. And with relapsing remitting disease, an individual will, if you look at their disability over time, the individual will have no disease, then they have disease symptoms, and again, those can vary in terms of could be eye problems, could be mobility problems, but basically they will have these disease symptoms and then they get better. So it's relapsing and remitting. And then later, perhaps, depends upon the individual, a month later, could be years later, they will have another exacerbation of disease and then they get better again. So this is relapsing remitting disease. And commonly what happens is that people will move from relapsing remitting disease to what's called secondary progressive disease. And in this case, the individual is no longer seeing these relapsing and remitting patterns of disease, but instead they're showing progression of disease disability. So they're increasing disability over time. So if you look at some of the characteristic features of multiple sclerosis, if you look at this slide on the top left, you see that this is a brain with the white matter of the brain, which is the white matter is due to the myelin. And what we see in the white matter of this individual is a lesion of demyelination, and this is characteristic of multiple sclerosis. If we look at the histology of the brain by microscopy, what we'll see is vessels, and here we see the red blood cells in a vessel. We see relatively normal brain tissue around the perimeter here, but what we see around this vessel are a number of very darkly stained cells. These are the immune cells that are actually moving from the vasculature into the brain, and these are the cells that are going to cause the multiple sclerosis. I mentioned that multiple sclerosis has been difficult to diagnose. Fortunately, with advancing research, we have tools like magnetic resonance imagery, or MRI, and that's shown here on the right. And what you see with this MRI of the brain of an individual with MS, most of the tissue, the black and gray, is normal brain tissue, but we also see these white regions. These are lesions in the brain of the multiple sclerosis patient. So this is very helpful in diagnosing disease. It's also important to note that the processes that we observe in multiple sclerosis are also characteristic of a number of neurodegenerative diseases, like Alzheimer's disease, Parkinson's disease, and ALS, or Lou Gehrig's disease. So anything that we can find in controlling these immune responses in the brain that will help with multiple sclerosis can also potentially help with these other diseases. When I first started working on multiple sclerosis maybe 20 years ago, there were no effective drugs, and this was very difficult, obviously, for the patients, but also for the clinicians as well. There's now a number of drugs that have been approved by the FDA for treatment of MS, and these are effective in slowing the progression of disease, and that's very helpful. But there are problems with the drugs that are available now. They're not terribly specific. They tend to suppress the immune system fairly globally, and we don't want that because there's problems like development of cancer if you don't have an effective immune system. And we are looking at the molecular mechanisms, the pathways that are involved in the processes, because then we can target those pathways and more specifically block the disease, as opposed to the more global immunosuppressive drugs that are available. Another goal and another thing that we're working on is that we need to move forward. We do have some drugs that are useful in suppressing the immune activity, but we also need to be able to repair. We need to be able to repair the damage that has already occurred. So we are in the process of looking at new medications that will then be involved in repair of the axons and repair of the central nervous system. And the ultimate goal is to cure MS. Any scientist working on a disease, they should be working towards the cure.